Hello, welcome back to the QuadTree project. So this project was essentially a way to derive the QuadTree data structure completely from scratch in C++ and to display it using the SFML library. So if you haven't watched the previous videos, the QuadTree is essentially a data structure where you can hold spatial data. It's a really useful way to query neighborhoods of spatial information. So if you have a bunch of points, in this case, the point will have X and Y location. So if you're calculating interactions between each of these points, you need to know how many points are near a point of interest and how many of them are really far away that you don't care about the interactions. So in this way, the QuadTree data structure makes it really easy to query which points are close and which points are further away. And the way it basically works, if I render this and run it, the data structure essentially allows you to add points to the global domain if the number of points that you've added exceeds some capacity. In this case, we've defined that capacity to be 5. It's going to subdivide that domain into 4 quadrants. And as you add more and more points to those quadrants will continue to subdivide, and so on and so forth, until each element of this QuadTree only has up to that capacity number of points. So in this case, 5. And in this case, in the last episode, we took our QuadTree data structure, we took our rendering of it and optimized it by essentially reducing the number of draw calls. So we had a separate draw call for every single line in this display of the QuadTree. And so what we did was actually optimize it so that we buffered all of the separate lines into one vector, and then we drew all of those lines all at once. And this means that, as you can see in the background, the rendering of this QuadTree, there's 5,000 points in this QuadTree, as you can see over here. The rendering of this QuadTree is only taking on the order of 2 milliseconds or so. So that includes all of the QuadTree lines and all of the points themselves. So that's great. Okay, so let's close this. So what I want to do today is to actually improve this. So rather than, let me actually display it again. So here you see that the points are actually really difficult to see. They're really, really tiny because we're rendering each point as a single pixel. We want a little more agency over that. So we're going to update the rendering of this so that the points are actually discrete circles. And we're also going to dynamically modify the QuadTree on the fly, so allow these points to move and evolve, which means that as the point moves from one node to another node, it has to be dereferenced from the first node and then added to the second node. So we're going to build both of these systems today. So if you remember from the previous episodes, the main event loop was happening here. So while the window is open, it's going to essentially pull for events over here. This was our simple way of adding points by using a mouse click. But the part that we're actually interested in right now is this rendering of the points. So just to show you what this looks like, we're basically taking our vector of points. Remember, in this case, this is 5,000 points. And we're creating a new data structure that is purely SFML based. So this is a vector of all of the SFML vertices, which is just the point data on in the pixel space of what these vertices look like, of what the point looks like. And for each point in our global vector of points, we're essentially converting it from our world space, which, if you remember, our world space was between 0 to 25. But our pixel space is between 0 to 600. So we're transforming to that pixel space, and we're converting from the point XY coordinate system into the SFML window XY system, putting the color for these pixels, and then using one single draw call to draw all of these pixels. And we're using the type of a point, which is basically going to render each of these independent vertices as independent points. As opposed to something like the actual QuadTree. So this is our render QuadTree function up here. And what we're doing here is to use the exact same method, but we're going to render these as lines instead. And the lines data type essentially takes 2 sets of points and draws a line between them. In this case, for each QuadTree, we're actually adding 4 sets of lines or 8 sets of points, where these 2 points define the left edge of the QuadTree node. These are the top edges. This is the right edge, and this is the left edge. So this set of 8 points is actually rendering one QuadTree square. And so we're going to borrow basically this idea and render our point as a series of discrete lines, which when you're looking at it from far away will look like a circle. So the first things first is to define what the resolution of that circle is going to be, and hold, very similarly to this, hold a vector of points. Let's do that. So let's create a vector very similar to this of vertices, and this is going to be the point circle lines, like so. Let's also define the number of points per line per circle. And this is, we don't need to be too egregious. This can just be something like 16. So let's basically follow the same paradigm as the QuadTree. So what we need to do is to add pairs of points so that it encompasses 16 points in a circle. Okay, so we don't actually need this right now, so I'm going to comment this out. We don't need this because we're not actually rendering, we're not actually using the old vertex data. And then in the end, we actually want to, instead of vertices, we're actually rendering the point circle lines. Point circle lines, like so. And we're not rendering points, we're rendering lines. Great. So the first things first is let's actually resize our point vector lines. So this is going to be the total number of points, drawable points that we're going to create. And so this is going to be points.size times, remember we need 2 points per line, so times 2, and we have n points per circle per point, right? So going forward, I'm going to start referring to the circle as the rendered point, and then the point as the actual data. So for each point, we're going to loop over the 16 unique vertices. We need 3 attributes here. We need the X and Y position and also the angle around the circle, which will be used to define that X and Y circle position. So the angle is just going to be 2 pi over n points per circle. So this is the resolution, angular resolution of the circle, times, and we're just going to cast the I into a double, like so. Why is it not detecting n pi? Probably need the library. Yeah, I need the CMath library. Great. Okay. Cool. So now we have our angle. Our x is just going to be the cosine of this angle times we need to define a point radius or circle radius. Let's call it point circle radius. And then we're going to shift this in our world space by the point's x value. So we're going to do something very similar for the y value, except it's going to be sine of the angle and then point y. So up here, let's define again the point circle radius, and this can be 5. So remember that this is in our world space. Okay, so then 5 is actually really high. So let's do 0.1. Just to compare, our domain is 0 to 25. We're fitting 600 points across this, so the resolution is essentially something like it's less than 0.1. So 0.1 should be more than enough to actually see the line. So we're not going below the resolution of the window. Great. Okay, so now we have our x and y position, and now we need to render 2 points per line. And we can be smart about this because we're doing this calculation here. We only need to do it. Well, let's try to optimize it on the fly so that we're only doing one of these calculations at each time. And so the way we're adding this is actually, so imagine this is what our vector finally will look like. So assume that 0, 0 is that first point, right? And then our next one is going to be 0, 0 0.5, 0, 0.01, and then the next is 0, 1.5, so on and so forth. So these are the actual points. And the way that the line is being rendered is that we need to duplicate this line, this value each time. So 0, 0.5 means that it's going to render one line between these two, and we need the 0, 1 again. This means that it will draw 3 separate lines between 0 and 1.5. And so what we can do is actually duplicate this, because you see that the first point and the last point are here only once, but then every other point is being rendered twice. So actually we can flip this data structure so that it does this instead, which means that if I equals 0, if I is not equal to 0 and I is not equal to n points per circle minus 1, not equals, then we don't need to duplicate it. If it's any of these two, if I is 0 or I is equal to n points per circle minus 1, we don't need to duplicate. There's only one of each, one here and one here. But every other time, we actually need to duplicate it. So let's first create the first at the first point. So what we're going to do is push back. Remember, this is in the world space, so we need to transform to pixel space, and this is going to be a vector 2f. This actually needs to be a okay. So vector 2f, this is just going to be x and y, and then this needs to be the color of our line, like so. Transform to pixel space. Oh, I see. That's because that's wrong. So we need to transform this like so. Yeah, there you go. So this is our first line. So if it's not the first point or the first vertex or the last vertex, we basically need to add this twice. And I think that should be it. And again, the logic here is that if it's the first vertex, you don't need to add it twice. But if it's the second vertex, you're going to add it twice so that it renders one line between these two, and then one line between these two. And if it's the last vertex, you don't need to add it twice because it's again one line between these two. So with this, you don't actually have to calculate x and y twice per loop. But let's just test this out. So let me remove this. Let's see if we run into any issues here. Okay, it rendered without an issue. Oh, that seems to work. So we actually don't. Let's not have 5,000 points. Let's just have 50 points. Okay, so here's our 50 points. It does seem to be circles, except it's not actually rendering. Let me make this bigger so you can see what's actually happening. It doesn't seem to be rendering the last vertex. Yeah, you can see that's basically open hole. So we need to repeat the last line twice. That basically is adding back the first and the last point in the line. Cool, but this works. If I click, it adds a new point, which is great. The rendering is also still really fast, so we're not actually wasting time. So what we need to do is to add back. So this is adding what we have is actually, if I draw this again, so we have our 0, 0, we have our 0, 0.1, 0, 0.1, 0, 0.2, 0, 0.2, and then let me just add one more. Okay, so what's actually happening here is this is correct. What we're actually doing programmatically is adding the first point once and the last point once. But what it's actually doing is creating a line between the first and second point, second and third point, third and fourth point, and so on and so forth. But what we really need to do is to add this again, and then we need to add 0, 0. So it loops back in on itself. To do that, what we need to do is remove this. there's a smart way to do this, and then there's the hacky way to do this. The hacky way would be to actually do this twice, like so, and then roll the vertex. But I think that's too complicated. So it might actually just be simpler to add back the first point again. So this is actually adding this last point again. So what I might do is we know. Okay, let's see. What we know is we've added if in this case n is 1, 2, 3, 4, 5, 5. So n equals 5 here, right? So this is I equals 0. This is I equals 1. This is I equals 2. This is I equals 3. And this is I equals 4, right? So what we need to do is for I equals 4, we need to look up the point that was in I equals 0 and basically push it back. So down here, we just need to point circle lines dot push back, and we need point circle lines minus some number of points that we need to go, like so. So we basically take the basically the point that was at the very end and go back a certain number of points. Okay, so to do that, what we need to do is to actually calculate how many points this is. So this is right now here. Let's create a second column. Oh, sorry. Let's create a second column where n equals 0, n equals 1, n equals 2, n equals 3, n equals 5. Okay, so we are right now at n equals 8, and we just need to go back 8 steps. For n equals, for number of points equals 5, we've added 8 points. So this might be, we might just need to go back 2 times n points in a circle minus 1. Which makes sense because for each one we're adding 2, and we need to go back n minus 1 times. So let's see if this works. This might not work because I need to do this way. Point circle lines of size minus this. There we go. So for after we're done with our loop of all of these points, right? We're right now over here. What we need to do is to go back n minus 1 times 2 points and add back this original point again. Let's see if this works. This should not give me any errors. Great. Okay. And there we go. Yeah, that worked. So we're actually added all of our points again, and I'm still able to add new points. We're getting really good performance. I don't think there's any real reason to reduce the resolution or increase the resolution of this or even reduce it. Let's bump it up to 64 just to see how much that changes things. And I'll go back to 0.2 for this. So let's see how this looks. Great. Yeah, I think the points look good, and the frame time also looks pretty decent. Let's add back our 5,000 points. See if this still renders really quickly. I didn't do that. Okay. We're still rendering. We're rendering 5,000 points, but still at 2 milliseconds. I think at this number of points, I think I might reduce the radius a little bit. So let me do that really quickly. So 0.05, which is still, I think, bigger than the resolution. of the pixel resolution of the frame. Yeah, there you go. So we're still getting discrete points, which is great. But right, it's still taking 2 to 3 milliseconds, which is really awesome. And we're able to add more and more points as we go. What might actually help is increase the capacity of this. So rather than 5, I'm going to bump this up to 25, because we know that the actual QuadTree data structure is pretty fast, and that reduces somewhat the number of QuadTrees that we're rendering. So this is great. We have a bunch of points. We have a bunch of lines. So we're able to render this really quickly, and we're also able to see the actual points. If you wanted to fill this in, there's ways to do it. But at this point, I think I like the hollow circles. So we'll keep that for a future fix. Okay, so now the point is to actually start moving these. What we're going to do is to actually add an update function to the points, and we're going to basically have them move. Let's do that by creating a new file. Yeah, I think it might be easier if we keep this as a separate file, and let's call this interactions. Yeah, let's call this interactions for now. Like so, let's open up interactions.h. We'll do a pragma once clause up here, just so that we're not importing too many things. And for right now, we'll update things in place. So we'll do an update points method, which is just going to take in, just as how I've always shared it. It's just going to take in a std vector of, I forget, did I do unique pointers? I did share pointers of points, so we'll just do that. I think I need to import points. Okay. This is going to include I think point.h. Yes, I need to include maybe memory. Yeah, that works. This is just going to be a prototype. So in interactions, we're going to include interactions.h, and then we're going to actually define. We're going to define this function. So what I'm going to do is to actually give each of these points a velocity, like so. So we're going to keep that old method, and then also give it a method to include initialize the velocity, like so. In this case, we're going to initialize the vx and the vy's with 0. But in this case, we're going to initialize this with those initial velocities. Great. Like so, which means in the we might also need a, yeah, let's pass in the time step here. And so what we're basically going to do here, we'll just keep things very simple. For all of the point in the points, what we're going to do is just update the point.x is point.vx times .t. These are pointers. And then update the v. That's it. Like so. Great. Yeah, that should be very straightforward. Let's just see if they move. So here I am going to, we don't need QuadTree actually right now. We don't need render right now. So for each of these points, let's add a vx and a vy. So, and then we're going to do vx. Okay, and so down here, before we render the points, actually after we clear the So the way we we're doing it is we're going to keep all of our physics up here before we clear the window. We're going to clear the window and then update everything. So let's just stick to that idea. So we're going to update the points, and this is just going to be the points. And we need to pass in the delta t, which I didn't put in here. And our delta t is just going to be a... do I want it to be a constant? No, let me put it here. So I think right after I define this, do that. And we can update the delta t if we really need to. So this shouldn't really, we haven't done anything new. So, ooh, there is a problem. Undefined reference to update. Oh, yeah, because we haven't included our interactions.cpp. Interactions. Yep, that worked. There you go. And now our points are actually moving, but the QuadTree isn't being updated, and the points kind of just disappear out of the window. So we need to do a couple of things. The first is to make sure that the points are confined within our QuadTree. The easiest way to do that is just add reflecting boundaries. So when we're updating our points, let's also pass in the bounds. It's going to be a const, like so. Const. So, and what we're going to do is if point x, I think if I remember correctly, our bounds had a contains method, but it doesn't actually tell us which direction it's going out of. Yeah, so it doesn't tell us which direction it's going out of. So what I'm going to do is to actually re-render this myself. So if it's greater than this, then we're going to reverse the velocities, like so. It's fine if in this time step it's slightly outside. We'll deal with that problem later on. Is less than bound.xmin. Oh, sorry, too much Python. There we go. Let's do that again with the x. Yes, that's correct, except for max. Great. This means that essentially the point should bounce back. So if it hits the left boundary, it should reverse its x velocity. So if it's going in the positive direction, it should reverse it. If it's hitting the bounce x max, it's probably moving to the right. There's no other reason it should do that, so it'll move to the left instead. You could enforce this by putting an absolute value here, but it's fine. Let's clear this out. There you go. So things are moving way too fast. So I think our velocities are too high. Yeah, our velocities are a little too high. Let's bound our velocities a little bit by a factor of maybe 10. There we go. Things are moving a little slowly. I think the distribution is bounded by 0 to 1, so that's why everything's moving to the right. But it looks like they're bounded. Nothing seems to be escaping. You can see that it overshoots a little bit, but for the most part, things are bounded. So now our points are moving. Here, let's do something while we're here. Let's fix this first. So let's shift this by a factor of 0.5. So it's between negative 0.5 and positive 0.5. Remember that our distribution, our uniform distribution is going to give us, our uniform distribution is going to give us a value between 0 to 25. I see. Okay, so let's create another version of this where it's the velocity distribution. let's bound this between -1 and 1. And so this means that we're going to use our velocity distribution here. We don't need this. We don't need this. I don't think we need the divide by 10 anymore because we're bounded by -1 to 1. Great. So this should give us a value between -1 and 1. And what I'm going to do here, I'm going to create two Boolean flags. Render QuadTree and render yeah, let's just call it render QuadTree and then render. So and here, if event.type equals e pressed, and I think if event dot e dot e yeah, we're gonna flip render qt equals not. So is e dot code. I think that's correct. I can check this again. So just to look through what that looks like. Ooh, the SFML a little slow. Processing events, key pressed events. Yeah, okay. So key events, key pressed, event.key.code contains the code. And I think we just compare it to, yeah, we just compare it to which key it was. I think that should work. So it looks like it's not keyboard.t, so it's key, maybe an older reference. So let's set these to true first initially. Then we're going to duplicate this, and we'll do p instead for the points. So what this is basically saying is if I press P, it toggles the rendering of the tree, the quad tree. If I press P, it toggles the rendering of the points. So I need to actually move this down here. So we were not actually getting the performance of the points actually. So if render quad tree, we should do that. If render, we should do that. Let's see. That actually might change our frame time a little bit. Oh yeah, our frame time is significantly slower. But now if I press T, it should remove the rendering of the quad tree. If I press P, it should remove the rendering of the points. And yeah, as you can see, the rendering of the points is much slower. This might be because I added. Go back to render. Yeah, I think it's because I added 64 points. So let's change that to 16. Let's actually reduce that to 8. Yeah, there you go. Now we're actually moving. We're whizzing by. The points are moving fairly randomly. There's absolutely no interaction between the points. They're not colliding or anything, but they are bouncing against the walls. So things are being updated really quickly, but you can see that the quad tree structure is still uniform. So it's not actually updating to grow with the growing set of points. So that's what our main goal today is. So let's clear this out. And so what we really need to do is we've updated our points here. What we need to know is which of these points have moved outside of the QuadTree that they're currently in. And if they have moved, we should add them back. So it's fairly easy to figure out which of the points have moved. Because we just loop over the points and then we figure out which ones are not in the belt. So let's create that out first. We'll build everything in the main loop and then we'll move them to their appropriate structures. So for point in points, maybe we should do QuadTree's points. Yeah, let's loop over the QuadTree's points. Actually, let's do it this way. So what we're gonna do is for let's loop backwards. So points dot size -1. Right, and so what we're going to do is for each of these points, we need the step to check the steps to update as follows. I don't know why it's doing that. So the first step is we need to check if the point is still in the old leaf node. Step 2, if it is, we're done. If it is not, then remove it from the QuadTree and add it back. And the reason we just remove it and add it back is if we remove it, then it's removed from that leaf node. And then when we add it back, it's going to go through the full cycle of figuring out what the new leaf node is where it needs to be added. Again, we're assuming that the actual algorithm for figuring out which leaf node to add to is really quick. In most cases it is. So we can brute force this. There's probably more elegant ways of figuring out what is the new leaf node. But at this point, the complexity is just not worth it. So we're just going to remove it from the QuadTree. So it removes the capacity of that leaf node, and then we add the point back. Okay, so let's do step 1 first. The first thing we need to do is to figure out if the complexity here is the fact that the QuadTree's points is going to be empty. So maybe rather than looping over every point, we need to loop over every node recursively. And we fetch back the points which need to be removed. Yeah, I think so. I think this actually should go into the QuadTree. Yeah, so let's move this in there for now, and we're gonna call this just update points, like so. And this is fine because the points is actually part of this. But the issue is that if the QuadTree is divided, we're going to loop through what do I call it? Leaves. 8 points. So why is it? Because it's a unique pointer. Okay. So what we actually need is How did I do it before? I just did the, okay, let's just copy this. So what it's going to do is if the quad tree is divided, it's going to call the leaves. It's going to keep doing that until there are no subdivisions, at which point it's actually going to loop through the points. And remember that the way we've distributed our quad tree, all of the points are located at the leaves node. The root node doesn't actually have any of the points if it's divided. So we're going to completely skip all of this for the root node, and then we're going to add it to the leaf node. But what we actually need to do is to create. We want a global list of points that we know that we've removed, and we need to add those points back because remember that we removed it from the quad tree here. We need to add it back to the quad tree. And we can't add it back on the same leaf node. We have to add it back at the root node of the quad tree. Which we don't want to recurse at this stage. What we want to do is to just figure out all of the points that we've removed. And then we're going to need to add those points back at the end once we've removed all of the points that we need. Okay, so there's probably ways to do that. Either the simplest way might be to, I think I store level. Yeah. So I could create a vector here, all of the points, and at level 0, I reset that vector and then add it back in. But I think the easier method, yeah, let's do that here actually. So points to remove, yeah, okay. So if level equals 0, this is the root node. Points to remove dot clear. So we're going to, at the root node, clear out the vector of points that we want to remove, and then add them as we iterate over the points. So step 1 is really easy. Step 1 is really easy. So if points of I, if this dot bounds dot contains this point, if it doesn't contain this point, we are just going to add this point to the point start remove pushback point, and then pop back. I don't think you need it. Yeah, you don't need to actually pass in. Shouldn't be. Oh, points of. This bounds. I think point needs to be. Yeah. So there you go. So we're going to remove it, and we're going to pop back, which means we're going to reduce. And remember, we're looping backwards. So that shouldn't affect the structure of the array. Okay, great. And so once the points are removed, we want to, what can happen is if there's only 5 points here, then we need to merge the, so let's say originally we had leaf nodes which were all full, so each of them had 5 particles. And let's say all of the 5 particles moved out of the leaf node from each one. That means that there are now only 0 particles in each of those leaf nodes, which means that we need to merge those leaf nodes back so that it becomes part of the parent node. So we need to check, actually we need 1.5 here. check if the leaf node needs to be merged. Leaf node needs to be. That's pretty simple to figure out if it if we do need to merge it. At least for the case of this, we want to see if I should do this. Actually, we shouldn't do this here. We should do this here. So once the leaf nodes update, we need to check if oh, we can do this here. So I keep forgetting that this is a vector pointer. If count is less than capacity, then we know we need to merge. So I don't think we have a function yet to merge. We only have a function to subdivide. So let's create a merge function really quickly. It's best if we keep this as a boolean. Yeah, we need the opposite. Basically, it's going to be the opposite of the move points to subtree function. There's actually a lot more complexity that we could add to this function, but for right now, let's just keep it as simple as possible. So we're going to assume that the only time we're calling this function is from update points. So right here, we update the points, we check the leaf nodes, we see if the leaf nodes are beyond some capacity, and if so, then we want to merge. So here we need to call this merge function, like so. Need to return out of this because we never want to do this part. That's right. Yeah. Okay, cool. So we just need to handle this merge function. So what we need to do is essentially take all of the individual points from leaf nodes. So let's just create a leaf points. So for point in leaves of I dot points. I don't know if that's a pointer. That should be a pointer. We're going to actually we should again we should no, that's fine. So leaf points dot pushback point, and then at the end of all of this we clear out leaves of I dot. And then we're actually we just need to delete the leaf. What did I say this as? A set of unique pointers. Yeah, I think I maybe don't even need to clear the leaves. Release, like so. This should call, well, should not release node at level. Really? Oh yeah. Okay, and at the end we just return true. So we take all of these points And what we need to do is to just add these back here. So we know that they belong to the right way to do this would be we need to add it back at the root node, but we know that these points belong to this domain because we've just checked it over here. We know that all of these points are actually within the bounds of the leaf nodes, so we can really just add these points back in. This points dot pushback, and we just need to push back these points. Since these are shared pointers, for one, they should always belong in the QuadTree up here. So they should always belong over here. By calling, where did it go? QuadTree message. By calling the clear over here, it actually moves the ownership to leaf points, which again moves the ownership here. So this is all completely fine. So we've called merge. We've called right number back here. If it's below the capacity, we should merge. And then finally, we should not return here because level 0 still needs to. Let's do an else here. Actually, that should work. That way we don't need to call return. Oh, really? Okay. Oh, I see. That's what happened. Okay. So if it's divided, he needs to do this. If it's not divided, he needs to do this. And the finally, if level 0, we're going to add those points back in. Is the what do I call it? Insert points. Insert. So if level is 0, then we just need to return. It's a void function, so we actually don't need to return. Great. So so level 0, we're going to clear out the points. It's going to loop through. Is that right? No, this is not right because because the ownership this vector is not shared between. So this needs to be a global vector basically. So we're going to move this up here like so. Find header file. Yeah, it's not the best way to do it. Let's do an extern and let's actually define this in QuadTree.c. Like so. Okay, so this is created here. It's a global variable. We are not doing multi-threaded data, so it's going to be updating this one at a time, which is fine. If we do end up trying to do any sort of multi-threaded stuff, we need to be really careful about adding these points to the vector. Ideally, it doesn't matter because the order of operations doesn't matter, but we want to make sure that there's no race conditions when we add things. But since this is now a global variable, all of the QuadTree nodes will have access to this variable, to this vector. So we should be fine. Let's just try to comparison of int to size t. Just size. Render.cb. Really? Update points. No, it's still QuadTree.h147. Okay. Cool. go. Let's see if this works. Okay, so we have way too many points. So what I'm going to do is make this only 25 points. And okay, let's do this. Let's try to see how we can figure out if this is correct. That divided. We'll see if anything changes. I don't know why it's adding a bunch of points there. We seem to have a bug in the code. Did I actually remove the points? I think I did. So let's do this. Let's create this at... Let's make all of these points move to the left. And we're going to start all of these points on the left as well. So uniformly distributed in Y, but let's keep these points moving from the left to the right. We only have 25 points. Let's do 50 points. So you see that we've subdivided here. Eventually, when they shift over, it is not merging. So this should have subdivided, and then this should have merged. There's something wrong with... Oh, that's because I'm on actually not called. Yeah, I'm not even calling the QuadTree update points. Ooh, seg fault. That's great. Let's see where it's seg faulted. Okay, so we have update points, invalid read of site. Okay, so we need to re-render this, the debug flag. QuadTree.h161. Oh, didn't mean to do that. Points of I. Oh, yeah, that's pretty stupid. It should be minus. I would use an iterator for this, but still have a seg fault. Still having an issue at 160. What are you complaining about? A 1520. I wonder if it's actually. I know erase takes in the position, so we could try to just erase whatever it is at that position. But I think I need to loop backwards. So let's try that. This points dot end it is not equal to, and then it should just be it. Right? Um, that works. We just need to push back this point. Oh, shouldn't it just be IP? Why not? Oh, from there you go. Yeah, that should work. So I'm looping over. It might have to be minus IT. So I switched over from the calculating this as looping over from end to beginning and just looping over, just actually using the vector iterator. Let's see if this works. So it gives us self quad. Okay. And at this point, it's actually not even. It's still giving us the issue here at 143. Oh, that is very strange. Do I not need to? Okay, let's forget about the actual erasing part. And let's just see if we're getting this to print out. We're having issues further up for. And loop the normal way. Seems I'm just like stupidly forgetting how to iterate over the vector. Oh no, it works. So that works. So there's still a segmentation fault. Um, that's strange. Let's print this out. Count stuff. Print out the capacity, which it's going to give us an error because it's not the right format. Let's just print this out. Yeah, let me print out the levels. It should not actually be removing point. So what's going on? Comment this out. Um, we should be adding way more than 28 points. We'll be adding 50 points. So, okay, so level. Twenty-two and 28, great. Those are good. Oh, I see. I see the issue because it's not actually. Sorry, we're in here. It's not actually counting the number of points with the subdivided nodes. Um, so what we actually need to do is if the leaves are subdivided, we should not merge. Essentially, right? We should be able to handle that logic here. If what we could do is be really smart about this, and actually, as part of the what we could do is to have this be an int. I mean, does this work? So here, if it's not, we just return. Um, move this up here. Yeah, there you go. So level 0 has count of 50. Level 1 has a count of 27. And that looks correct. So we can open this up again. Yep, level 0 has a count of 50, level 1 has a count of 27. Um, Great. So let's keep that as it is, and then let's uncomment this part out. Oh, okay, that's segfaulted. So it looks like that happened when it was actually trying to move over from one window to the other. Let's see if that works. I think I see the issue. We'll come back to this in just a second. Um, so what might be happening is we shouldn't be right. So we'll loop from the beginning to the end, like so. If we erase the point, the iterator stays at the same location. If not, we'll update the iterator. So basically, as we're looping from the beginning of the vector to the end, we're going to go through every single point. If it erases a point, the iterator just removes that point and then shifts to the next point in the vector. The iterator stays at the same location, but it's actually the next point. So let's try this. This might work. Oh, no, that also gave a segfault. Level 1 count is 0. This might be a different segfault. See where this crashed. So this crashed in QuadTree. Interesting. So whatever point it removed, we need to insert back in. Let's see if it's doing that. That, that. Removing those points, it's trying to insert this first point, 17517, and then that's giving a second. Why is that? Oh, right, because once we merge the points, when we merge here, we should set divided equals to divided to false. So let's see if this moves. There you go. So it moved over from the left node over to the right node. Aha, so that's actually a problem because it moved outside of the bounds of everything, actually. That's a little strange. Wonder why it did that. Let's see. It was back up here. Yeah, the issue is that these points are removed from the QuadTree because they're outside the bounds. Oh, that's a really annoying bug. Because what's happening is that they go outside the QuadTree and they're all removed from the points. And what we're doing here in update points is actually looping over only the points that are within the QuadTree. So if the point is outside the QuadTree, we're never adding it back in, which is unfortunate, which is a really stupid bug. Um, the best way to fix it is, we know that this is working, so I'm going to remove all of this stuff. The best way to fix that is in this interactions. Set point.x equals minus some small epsilon. And we can define this epsilon up here. Same thing, x min plus epsilon. Y x. That should fix it. It's really stupid tiny bug. Still printing the okay, great. Things are moving. Okay. Let's see when it hits the edge. Nope, it's still just maybe the epsilon is too small. Let's set it to -6. Point x equals bounds dot x max minus epsilon. Yeah, okay, that might actually work. There you go. Yeah, that fixed it. It's basically forcibly moving the points back into the domain. There's better ways to fix this. We should ideally check if the point doesn't belong in the domain and then add it back in later on. Keep a running track of which points are within the domain, which ones are not. But for now, let's just test our rendering for more particles. Let's see if this works. Okay, things seem to be working. The QuadTree is shifting and changing. And it seems to be fairly uniform throughout. Okay, there's definitely things that we should be able to clean up. So, for example, if I go back here to QuadTree, this is a really pretty terrible way of counting particles, and there's a pretty terrible way of merging it because the merge should not depend on calculations that we have before. We should make sure that whenever we do the merge, everything is correct. We should make sure that the actual count is smaller than the capacity and so on and so forth. But for the most part, this is good. Again, this is probably not the best way to count the particle sizes. We're just being overly optimizer heavy at this point. So with all that said, let me just bump up the number of particles that we have to something like 5,000 or maybe even 10,000. Let's see how this looks. And I think that's going to be the end of today. Let me do this. Let me, rather than doing a uniform distribution, let's do a normal distribution. And I think this is the mean of the standard deviation. So let's do 25. Sorry, no, 12.5. So let's center this with a spread of 5. Um, so this is going to be points exploding out from the center. So there you go. Actually, let me reduce the velocity distribution so that things are a little slower. And you can see how the QuadTree grows as we bump up the number of particles. Okay, I think the initial distribution was really high. So let me try that again. Rather than 5, let's do 1. There you go. Initially, all of the points are bunched up together, but then they slowly spread outwards. And as they spread outwards, the QuadTree grows and grows, and eventually it starts filling up the entire domain. So this is essentially what we want. Ideally, if you're trying to do particle interactions between something like here and something down here, the number of particles that are here and here are so far apart and so few in quantity that it really should not take up a lot of computational time. You'll see actually the opposite is going to happen where the density of points over here decreases. So we're going to see more QuadTree nodes out to the edges and less towards the center, and then it's going to rinse and repeat. So we're able to dynamically update our QuadTree. We're able to figure out how many particles should go into which location. We can actually calculate densities based on this pretty well. So with all of that said, I think this is the end of this episode. It's been a long episode and a lot of fixing bugs rather than implementing new things. I hope you enjoy, and I'll see you in the next one.